Okay, so last class we have discussed some basics about fluid mechanics. Okay, so first let me summarize all those things. Okay, so we have already told that the fluid mechanics is a branch of mechanics itself. Okay, which deals with the bodies at fluid, which will be at a rest or in motion. Okay, both are there. Some will be at rest or some will be motion. Both the criteria they will be considered. Hello. Okay, then so when it is at rest, we say it as statics. So when it is at motion, we say it as dynamics. Okay. So when it comes to fluid mechanics, okay. So when the behavior of fluid is at rest, we say it as fluid statics, and when it is in motion, we name it as fluid dynamics. Okay. Then the study of fluid at rest is known as what? Fluid statics. So then we have studied the definition of fluid mechanics. The study of fluids in motion when pressure forces are not considered is known as fluid kinematics, and if the pressure forces are also considered, then the branch becomes fluid dynamics. Okay, so fluid itself, there are so many types of fluid that we have already discussed. Okay, one of the subcategory of fluid is hydraulics. Okay, what we say hydraulics, this technology what we use in lift or hydraulic ram. Okay, JCB, etc. Okay, these technology, hydraulic technologies. Okay, it is an also a category of fluid only. Also, I have told you in the last class we have already discussed gas and liquids. They both are considered as fluids. Okay, so gas dynamics is also the flow of fluid which undergo significant density changes, such as flow of gases through nozzles at high speeds. Okay, so this is there is a subject in engineering known as CFF. Okay, so this is the basically what we deal with is gas dynamics. Okay, compressed fluid flow. Okay, so basically it deals with gas dynamics. Okay, so another category is aerodynamics, in which we consider the flow of gases. For example, aircraft, rockets, automobiles at high and low speeds. They are considered as aerodynamics. Okay. Also, we have got specialized branches like meteorology, then not meteorology, meteorology, then oceanography, hydrology. Okay. They also deals with the fluids. Okay. So these are the basic things what we are studying about fluids. So last class we have studied some basic things about fluid. Now we are going in deep about what are the fluids and what are the conditions or what are the cases we can study. So we can basically say fluid is a substance which can exist in three phases: solid, liquid, or gas. Okay, but actually basically we deal with what? Liquid or gas phase. Okay, you have to understand that a fluid is a substance. You can understand, first thing you can understand that fluid is a substance which can exist in liquid as well as gaseous phase. But sorry, solid, liquid, and gaseous phase. But we will be generally discussing about liquid and gaseous phase. Okay. Then this is water fluid. Okay, there is a constant shear stress, there is a deformed rub, so the shear strain will be there. So when a constant shear force is applied, the solid eventually stops deforming at some fixed strain angle, where the fluid never stops deforming and approaches a certain rate of strain. Okay, if it is a, what is the specialty of a fluid is that when a shear force is applied to a fluid, it does not stop deforming, it will always deform. Okay, that is specialty, when it will be always deforming. Okay, and approach a certain rate of strain. Okay, that is the specialty of a fluid. Okay, but in solid it will approach a value. Okay, but in case of fluid it will not approach, it will be always there will be a strain. But in case of solid, a strain, maximum strain will be there, after that failure will happen. But in case of fluid it is not that the case, it never stops deforming and approaches a certain rate of strain. So we have studied it in liquid. Okay, molecules can move relative to each other, but the volume remains constant because of strong cohesive force between the molecules. As a result, liquid takes place the shape of that container. Okay, but the case is different with gas. We have discussed in the last class itself. Okay, on the gas, expands until it encounters the wall of the container. If there is a wall of the, only a little bit of gas is filled, and if you are providing a lid of the container here, the gas will expand up to here. Okay, that's specialty. Okay, and it will fill the entire space. Okay, this is because gas molecules are widely spaced and cohesive force between them are very small. Unlike liquid, gases cannot form a free surface. Unlike liquid, the gases cannot form a free surface. Okay, so what is the difference between liquid and gases? This also we have discussed in the last class. In liquid is difficult to compress, but gas what we can easily compress. Okay, liquid what occupies a fixed volume will not change the shape of the container. No fixed volume for gases. Okay, a free surface is formed if the volume of the container is greater than the liquid. Complete fill the vessel. Okay, no free surface will be there. Okay, in case of gas. Okay, so if gas is there, if it is filled in a container, it will fully fill the container. Okay. So now we are going to discuss. So we have just basically told about fluid mechanics in the last class. So and basically what is the difference, and we have studied about viscosity, etc. Viscosity means what? The resistance to flow. These things we have discussed in the last class. So today we will be studying about what are the application areas of fluid mechanics, or why fluid mechanics is important. Okay, so mechanics of fluid is extremely important in many areas of engineering and science. You have to understand that the fluid mechanics is very important in many areas of engineering and science. First one is biomechanics. Biomechanics means blood flow through arteries and veins. Okay, biomechanics. Then air flow in the lungs, flow through cerebral fluid. Okay, these are very important when you consider human body. Okay, the application of fluid. Okay. Then when it comes to household category, you can see the piping system of cold water, natural gas, and sewage, piping and ducting network of heating and air conditioning system, then refrigerator, vacuum cleaner, dishwasher, washing machine, water meter, natural gas meter, air conditioner, radiator, etc. So refrigerator, this has applications at our home. Vacuum cleaner has an application at our home. Dishwasher, automatic dishwasher also, now it's there. Then washing machine is another application. Then water meter is another application. Natural gas, that means our LPG gas. Hello? Hello? Any doubt? Then air conditioner that we use at our homes. Then radiator of the vehicles. These all has applications related to fluid. Okay. Then meteorology and ocean. That means when it comes to ocean, there is a branch known as ocean engineering. Okay, that's an important category, ocean engineering. So the ocean engineering, what they do is they will be studying the movement of air current and water current. Okay, that means what is the movement of air and water in the ocean side, or that is the study what they are going on. That is ocean engineering. Okay, then when it comes to mechanical engineering, the fluid mechanics has applications in design of pumps, turbines, air conditioning equipments, pollution control equipments, etc. You have to understand that pumps application is there, turbines application is there, air conditioning equipment application is there, pollution control equipments also application is. Then also design and analysis of aircrafts, boats, submarines, rockets, jet engines, wind turbines, biomedical devices, cooling of electronic components, and the transportation of water, crude oil, and natural gas. Okay, these are where the application comes. Then in civil engineering, fluid plays a vital role, because when it comes to transportation of river sediments, pollution of air and water, design of piping system, flood control system. These are main category what they study in civil. Okay, so this is very important. And for mechanical engineers and civil engineers, this category, this fluid mechanics has very good importance. Okay, because the flow of fluids, they are considering the flow of fluids in their subject for mechanical as well as civil. Okay, so when it comes to chemical engineering, the importance is that they are called chemical processing plants. Okay, so design in chemical processing plants plays a very important role when it comes to what chemical engineering branch. Then now we are going to study about what are the application areas of fluid mechanics, where this application will be coming. Then turbo machines. Turbo machine means our pump turbine, fan, blower, propeller, etc. comes under which type of machines? Turbo machines. Pump, turbine, fan, blower, propeller, etc. comes under turbo machines. For military purpose, missile, aircraft, ship, underwater vehicle, dispersion of chemical agents, etc. Then automobile, IC engine, air conditioning, fuel flow, external aerodynamics. Medicine, heart assist disease, artificial heart valve, lab on chip level, glucose monitor, control drug delivery. Then electronics, convective cooling of generated heat. Energy, combustor, burner, okay, boiler, gas, hydro and wind energy. Oil and gas, pipeline, valve, offshore rig, oil spill, cleanup, etc. Okay, these are the category which comes under oil and gas. So we can see from these applications, when you see its application comes under turbo machinery. So turbo machine means these are pump is all available in our home. Turbines turbines are hello. Turbines are there in companies for their day-to-day life. Fan, blower, etc. Then military, we have in missile, aircraft, ship, etc. Then automobile, IC engines, air conditioning, fuel flow, etc. Then medicine, there are so many categories: heart assist disease, then artificial heart valve, etc. Then electronics, convective cooling of generated heat, then energy, combustion, burner, boiler, gas, hydro, in wind power, etc. Oil and gas, pipeline, pump, valve, offshore rig, oil spill, cleanup, etc. Okay. So when you see this category, you may find that in almost all categories, this has got an application. So you can see missile aerodynamics, then automobile aerodynamics. You may see when you say that a car body, it will be designed on the basis of aerodynamics. Okay, it will be designed on the basis of aerodynamics. You have to understand that the number of fluid engineering applications enormous: breathing, blood flow, swimming, pumps, fans, turbines, airplanes, ships, rivers, windmills, pipes, missiles, iceberg, engines, filter, jets, sprinklers, etc. Then when you think about it, almost everything in the planet either is a fluid or moves with or near to fluid. So you may see this here, okay, this figure. So the shape of the car body depends upon the aerodynamics. Okay, that means the flow of air should be in a good surface through the vehicle. Okay, so that is what there will be a good airflow when the car is moving towards forward direction. Okay, it has to go through the air in the atmosphere. So the aerodynamics has to be balanced, then only it can move. Okay, similarly, it is the condition with missile. Then high-speed trains, then wind turbines we can see, then smoke from the factories. Okay, then pollution dispersion over the city. Then you may see so many examples: propeller, centrifugal pump, fan, jet engine propulsion, cross flow fan, etc. Okay, so then you can see here some more examples: sky jumping, golf, swimming, football, cycling, IndyCar racing. Okay, you may see these all these examples over here. Okay, you can find. Okay, I will share this PPT. In that PPT, you can go through. This all comes under the application of fluid mechanics. Then, how can you classify the fluid flows? Okay, so one is viscous flow, another one is that means what do you mean by viscous flow or non-viscous flow? It is known as inviscid flow. Okay, so when two layers move relative to each other, a friction force develops between them, and slower the layer tries to slow down the faster layer. Okay, so the internal resistance that we have already studied, what is viscosity? Okay, the internal resistance offered by the fluid flow is known as viscosity. So I have told you in the last class itself, if there is a layer like this, if there is another layer like this, if this is moving, the layer above this will try to slow down this movement. Okay, it will go friction, it will slow down. This is known as its viscosity. Okay, so we can say it is the internal resistance between the two fluid layers. Okay, so viscous flow means when there is a flow, when there is fluid there is a viscosity for flow. That type of fluids are known as viscous flow. Okay. So, however, in many flow of practical interest, there are regions where viscous flow are negligibly small compared to inertia and pressure force. If you are neglecting the viscous flow, it is known as inviscid flow. Okay. So, viscous flow means, I have told you what is viscosity. It is the internal resistance offered by the two layers of a fluid in flow. Okay. Or the resistance offered by a fluid flow is known as viscosity. Okay. So, fluids in which frictional effects are significant are known as viscous flow. If the viscosity is there in the flow or the frictional effect is there in the flow, that type of flow is known as viscous flow. So, these are the difference between viscous flow. So, you can see in viscous flow, there will be a frictional resistance. Okay. But when it comes to in viscous flow, the inertia force will be more. Then what you see is classifications internal and external flow. Okay. So if a flow is happening through a pipe, if water is flowing through a pipe, this is known as internal flow. Okay. 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 So if it is not unbound, if it is flowing through a surface, it is known as external flow. Okay. So flow through pipe is an example for internal flow. Okay. Airflow is an example for external flow. Okay. So to understand that when water is flowing through a pipe, it is considered as internal flow. And when it is passing through bowl or etc. or above the pipe etc. it is known as external flow. Okay. Internal flow means there will be a closing and the water will be flowing through that closing area. Then compressible and incompressible flow. Incompressible means the fluid is said to be incompressible means density will be constant throughout. That is known as incompressible flow. If the density is constant throughout, it is known as what? Incompressible flow. Okay. So if the density of the flow is constant throughout, it is known as what? Incompressible flow. Okay. So that means volume will remain constant. Okay. So density of liquids are essentially constant. Thus, the flow of liquid is typically incompressible. So therefore, the liquids are usually referred as incompressible flow. Okay, you have to understand that if the density of the flow is constant, it is known as incompressible flow. Okay, but when you can compress that, so for example, gases. For example, what is specialty of gases? When we can apply force, we can compress the gas. That type of flow is known as compressible flow. And I have told you there is a subject relating to compressible flow, compressible fluid flow, that is really dealing with the gases. Okay. So there are so many categories or numbers, constant numbers dealing with this fluid flow. Okay. So last class we have discussed about laminar versus turbulent flow. So laminar flow means you can see it will be a layer flow. Okay. When the flow is in a layer region, it is known as laminar flow. But turbulent means what can wave of a sea can be named as turbulent flow. Okay. If it is between laminar and turbulent, it is known as transition flow. Okay. So these are the three types of flow basically known as. One is laminar means layer by layer flow, and turbulent means wavy form, and transition means it will be between laminar and turbulent flow. Okay. That is a specialty. So this is the figure you can see. Okay. Then another type of flow is natural versus forced flow. Okay. So if you are making the water to flow with the help of some force, it is known as forced flow. And if the water is flowing naturally, it is known as natural flow. Okay. To understand that when you are applying a force for the flow of water or fan, for example, air, etc., or fan, pump, etc., are the examples of a forced flow. Whereas if the water is flowing naturally, it is known as what? Natural flow. Okay, that's the specialty between natural flow and forced flow. Then you can go into the next category, which is known as steady versus unsteady flow. Okay. So that steady means the no change at any point of time. The flow has no change at any point of time. That is known as steady. Okay, if it changes, what happens? It is known as unsteady flow. Okay, so steady flow can be also known as uniform flow. But if there is any change in the flow at any time, it is known as unsteady flow. Any doubt? Then we have last class we have discussed this intensive and extensive property. So I think we should not go this. I have told you intensive property does not depend upon the mass of the system, but extensive properties depends upon the mass of the system. We have already discussed this in the last class. Okay. Then density also we have discussed. Density of fluid is mass by volume. Density is always represented by mass by volume. Density is equal to mass by volume. Okay. Then we have studied this also. Specific weight is equal to weight of fluid divided by volume of fluid. Okay. Then specific volume is volume of fluid divided by mass of fluid. Okay. Then as properties of fluid, specific gravity. Specific gravity means weight density of liquid divided by weight density of water. Then specific gravity for gas is weight density of gas divided by weight density of air. So for liquids, we will be taking water as the constant value, whereas for gases, air is taken as the constant value. Okay. Then these are some problems, but
sir, what is the volume of water?
volume.
Now you say me that this is a specific constant value for the water has taken.
Oh, that is not
for
volume. That is not volume. I will explain that. Okay. Specific
Uh-huh.
gravity means weight density of liquid by weight density of water. Okay. So weight density of water is nothing but specific gravity into 1000 into 9,000 is the density of water. Okay.
This is in the notes, sir. This value we have in the notes.
Yeah. You can see over here.
And for the air?
Hello?
Sir, I was saying
1.004. 1.004. That is also there.
Yeah. Okay. Thank you so much. Thank you.
Mercury, it is 13.6. Okay. For mercury, it is 13.6. So you have to multiply. So the density will be 13.6 into 1000. So 13600 kilogram per meter cube is the density for mercury. Okay. So actually this mercury and water are the important things when it comes to this thing. Okay. So viscosity we have already discussed. It is the property of a fluid which offers resistance to the movement of one layer of fluid to the another layer. Okay, you have to understand that when a fluid is flowing through the surface, it has different layers. Okay, so different layers. So if this is the bottom layer, we can emit as 1. The other layer we can emit as 2. So there will be frictional resistance between 1 and 2. 1 and 2. This frictional resistance is termed as viscosity. Okay. Then we have already discussed these things in the last class. What we mean by Newtonian fluid. So what are Newtonian fluid? The fluid which obeys Newton's law of viscosity are known as Newtonian fluid, and which do not obey Newton's law of viscosity are known as non-Newtonian fluid. So what is Newton's law of viscosity? Some of you might have been there in the last class, so I will explain what is Newton's law. It states that tau is equal to mu into du by dy. This is the equation for Newton's law of viscosity, or it states that tau is directly proportional to rate of change of velocity with respect to y. Okay, the shear stress is proportional to rate of change of velocity with respect to y, and tau, when you have to remove this proportionality sign, we will be adding a constant that is known as mu. Okay, so this mu is known as constant of proportionality, or known as coefficient of dynamic viscosity, or simply we name it as viscosity. These are the things what we are going to study. Then we have already studied ideal fluid, real fluid, Newtonian fluid, and non-Newtonian fluid in the last class. Okay, so ideal fluid is one which is incompressible, but it is not practically possible. Okay, that means it is incompressible and is having no viscosity. Every fluid will be having some amount of viscosity, so we cannot say it is an ideal fluid. So ideal fluid is a concept only. So real fluid will be one which will be having viscosity. Okay. Newtonian fluid is a fluid in which shear stress is directly proportional to rate of shear strain, that we have already discussed, which obeys Newton's law of viscosity is known as Newtonian fluid, and which do not obey Newton's law of is known as non-Newtonian fluid. Okay, so we have studied in the last class paint, etc. are the examples of non-Newtonian fluid. So this is the graph. This also we have explained in the last class. Next, what we are going to study is surface tension. Okay, so other things are problems that PPT I will share, but I don't think it's much important for you to solve these things. Okay, we will study the theory parts, which will be important for us. After that, in the next class, we will discuss some problems. Okay, so surface tension and capillarity. Okay, what do you mean by surface tension? That is what surface tension is defined as the tensile force acting on the surface of the liquid in which the contact with the gas or on the surface between two immiscible liquids such that contact surface behaves like a membrane under tension. Okay, surface tension means if you are having a fluid, if you are having a container like this, if there is a fluid over here, so this surface, okay, when as is defined as the tensile force acting on the surface of the liquid in contact. So this is the surface of that liquid, and above this, what is there? Gas is there. No, that means if you are exposing a open water to the surface, what happens? The layer above the topmost will be air only. No, so if you are keeping a container of water open to atmosphere, the above water layer will be gas or the air. Okay, so that is what surface tension is defined as tensile force acting on the surface of liquid in contact with gas. So here, what is here? The tensile force acting at this surface is known as surface tension. Okay, or if you are mixing two immiscible liquid, that means immiscible means which are not mixing. The two liquids which are not mixing, when you are mixing that, when you are keeping that liquid, so in the contact surface between that two liquids, their force, tensile force will be acting. That is known as its surface tension. Okay, so surface tension is caused due to unbalanced cohesive forces acting on the liquid molecules on the fluid surface, liquid molecules at the fluid surface. Okay, molecules in the interior of the fluid mass are surrounded by molecules that are attracted each other. However, molecules along the surface are subjected to net force towards the interior. Okay, so the apparent physical consequence of this unbalanced force along the surface is to create a hypothetical skin or membrane. So we can find that, we will be finding that a membrane will be created. Okay, so for example, a simple example is when you are boiling a milk, no, we may see some layer, no, in the above portion of that milk. That is an example for surface tension only. Okay, so you can see surface tension over here. So this molecule will be having tensile force to all the directions. Okay, so a tensile force may be considered acting in the plane of the surface along the line of surface. The intensity of molecular attraction per unit length along any line is known as called surface tension. In Greek length sigma, it is denoted by sigma. Surface tension is denoted by sigma. Okay. For example, we can see, when we are soaking this powder, that means soap powder in water, you may see a bubbles, no? Bubbles. Okay. These bubbles will be having surface tension with the water under the bubble. Okay. So you have seen, no, that thing. So this is known as surface tension. You may see these are bubbles in which the surface tensions are acting on the surface of that bubbles. Okay. So there are two cases. For a droplet, the surface tension is 2 sigma by r. For bubble, it is 4 sigma by r. Okay. So hollow bubble, like a soap bubble, is in the air, has two surface in contact with the air, one inside and another outside. Because if you are considering a soap bubble, you may see over here, this inside the soap bubble also tensile force will be there. Okay. Outside also tensile force will be there. So there are two contact surfaces. Okay, for example, but it is open means surface is like this only, but it is closed means inside also one contact is there, outside also one contact will be there. Okay. Then we are next term what we are going to study is capillarity. Okay. So capillarity is defined as so capillarity means if you are keeping a pipe over there, the rise or fall of water inside that tube, small tube, is known as its capillarity. So capillarity is defined as the phenomenon of rise or fall of liquid surface in a small tube relative to adjacent general level of liquid when the tube is held vertically in a liquid. So when a tube is held vertically in a liquid, there is a general level. So the rise of water above or below, when you consider about that general level, that is known as its capillarity. The rise of liquid surface is known as capillarity rise, while fall of liquid surface is known as capillarity depression. Okay. So the rise of liquid surface will be known as capillarity rise, whereas the fall is known as capillarity depression. Okay. The attraction between the wall of the tube and the liquid molecules is strong enough to overcome the mutual attraction of the molecules and pull them one. Hence, the liquid will said to have wet solid surface. Okay. So capillary rise is always expressed in centimeter or mm of liquid. Okay, that's a small rise only. Okay, you may see like this small rise of liquid. If the general level, there is a small rise of liquid over here. For example, if it is a 5 rise. Okay, so this is an example for capillarity, a small amount of rise or fall of liquid in a tube when we are keeping it in a water surface. Okay, that is known as capillarity. Okay, so the attraction between the walls of tube and the liquid molecules are strong enough to overcome the mutual attraction of molecules and pull them to the wall. Okay, so you may see this is the capillarity. So you may see after the capillarity rise has happened, capillary rise has happened, you can see when you see a fluid level, you may when you're approaching, when you're seeing a fluid level, always it will not be like this. Like there will be a small concave surface. Okay, like this. Small surface will be like this. No, it will not be straight. There will be a small depression always. Okay. So consider a glass tube of small diameter D. So this diameter is D, open to both ends and insert in a liquid. The liquid rise in the tube above the level. So H is the liquid rise. So this was our general level and this is the rise of liquid. Okay, that is what. So this rise is known as capillarity. Okay. So this rise of liquid is known as its capillarity. Okay. So the expression for capillary rate is 4 sigma divided by rho GD. That is the expression for capillarity. Okay. So when it is water, it will be like this. So if it is mercury, the shape will be like this. Okay. So you can see water, the meniscus will be like this only. Okay. For water, mercury will be above. Okay. So I think the concept is clear, no? So then you have to study about one more thing, one more basic thing, dimensions and units. Okay. So this is the what you see as dimension means. I have told you there are basic three units, basic units. What is mass, length, time, and temperature? Okay. So mass is always expressed in capital M, length as capital L, time as capital T, and temperature in theta. Okay. Or what is a degree Celsius? Okay. So kilogram in kg, meter. So this mass we are saying in kilogram, length in meter, second in temperature, and temperature, sorry, second time in second, and temperature in Kelvin. Okay, these are known as basic units. Okay, so last class we have discussed about basic units. So these are known as derived units. What is specialty of derived units? They are derived from the basic units. So you have to understand that what is specialty of derived units? They are derived from the basic units. So let me all of you please see here. Velocity is what? Velocity is what? What is velocity? Distance by time. Okay. What is distance? Distance is always expressed in meter. Time always in second. Meter per second will be unit. So meter, what is here? For meter, what is our symbol? L. L. Okay. What is the symbol for second? T. So since it is by L, T raised to -1, it's its dimension value. Dimension. What is it? It's a dimension. Why dimension came? Because meter per second. Meter is expressed in length and time in seconds. So you can see L T -1. Okay. So that is acceleration. Acceleration is nothing but velocity by time. Okay. So what is the dimension of velocity? LT -1. We have already discussed. What is again divided by time will come. So you can write it as LT raised to -2, because here when it comes to upward direction, it will be T -1. So it will become LT -2. Okay. So I think concept is clear now. How this came, this both came. Next is force. Force is F is equal to mg. Okay. So what is the unit? M is mass. Mass you have to express in m. What is g? G is acceleration due to gravity, or you can write F is equal to ma also you can write. So it is acceleration due to gravity. What was our equation of acceleration? Acceleration L T raised to -2. So what will be its dimension value? ML T raised to -2. Okay, concept is clear now. Any doubt? Pressure is also same as pressure and stress. Pressure and stress. What is pressure? Pressure is force by area. What is the dimension quantity of force? ML T raised to -2 divided by area. What is our area? Is meter square. That means L square will come. So when this L square go to upward direction, it will be M L -1 T raised to -2. Stress also force by area. So the same will come. M L raised to -1 T raised to -2. I think the concept is clear. What is density? Density is mass by volume. What is mass? M. Volume is what? Volume is length into breadth into height will give you the volume. So meter into meter into meter. So it will be meter cube. So meter cube means L cube will come. So M L raised to -3 will be the equation of density. So these are the things you can study. So similarly, viscosity is what? Viscosity we have already discussed. Viscosity mu. Tau by du by dy was your equation. Tau is shear stress. Shear stress, what is your stress? What is that? M L raised to -1 T raised to -2. Du by dy will be, you will be getting T will come. So that T, when it goes to up, 1 by T will come, 1 by T. So when it goes to upward direction, it will be T raised to 1. So this will become M L minus 1 T raised to minus 1. Okay. So similarly, you can study these things. These are very simple. I have told you, only thing is that first you have to study two types of quantities. One is basic quantity. Basic quantities are mass, length, time, and temperature. Mass is always expressed in kilogram, length in meter, time in second, temperature in Kelvin.
Temperature you want kilogram, mass in kilogram, length in a meter.
So when you after this, what you have to, the dimension, you have to study what are the dimensions. For mass, the dimension is M. For length, the dimension is L. Time, the dimension is T, and temperature, it is theta. So velocity, in the first thing is velocity. I have told you, velocity is length by or distance traveled by time. So distance is always expressed in meter. So what is the unit of meter? What is the dimension L? L by T. Time is T. So when this T goes to upward direction, it will be T raised to minus 1. Similarly, when you have these equations over here, just apply the dimension values, you will get the dimension point. Okay, I think the concept is clear for you. So we have written the table over here. So actually, SI unit, length in meter, mass in kilogram, time in second, temperature in degrees Celsius, force in Newton. Similarly, in earlier, foot was used. Okay, then slug was used. Second, Fahrenheit and pound. Now the standard what we are following is length in meter, mass in kilogram, time in second, temperature in Kelvin. That is the standard thing what we are following. Okay. So then what is 1 Newton? 1 Newton is nothing but force required to accelerate 1 kilogram of mass to 1 meter per second square. Okay. So what is force? Force. If 1 Newton force is nothing but 1 Newton force is nothing but it is the force required to accelerate 1 kilogram mass to 1 meter per second square. Okay, that is known as 1 Newton. Okay, so that is specialty. This 1 Newton is very important. So what is the equation of force? That is also important. F is equal to ma, mass into acceleration. From where we get this equation? It is derived from second law of Newton or Newton's second law. Newton's second law. Okay. So that is F is equal to ma, mass into acceleration. F is equal to ma, mass into acceleration. Okay. So these are another things. Density is mass by volume. Pressure is equal to force by area. Okay. So then, but next thing what we are going to study is Archimedes principle. Archimedes principle is nothing but, okay, when a body is partially, if there is a water body over here, if a body is partially or fully immersed in a water body, okay, partially or fully immersed in a water body, okay. So whatever is the immersed in a fluid is be buoyed up to the force equal to weight of the whatever force is there, it will be equal to the weight of water displaced. Okay. So a body fully or partially immersed in a fluid is buoyed up by a force equal to weight of the fluid that the body displays. Okay. That is Archimedes principle. Okay. So one thing is Pascal's principle states that a change of pressure applied in an enclosed compressible fluid is transmitted undiminished to every portion of the fluid to the walls of the containing vessel. So whatever pressure is there, it will be transmitted equal to all directions. That is what Pascal's law states. Okay. Bernoulli's theorem. What do you mean by Bernoulli's theorem? Bernoulli's theorem is nothing but, so you may see if this is a pipe like this, there is a datum over here. So if this height of this pipe is Z1, when you consider here, the pipe is Z2 over here. And if the pressure here is P1, and here the pressure is P2. Here the fluid is flowing at velocity V1. Here it is flowing at velocity V2. Then what we see is P by rho G, okay, plus V1 squared by 2G plus Z1 is equal to P by, is a constant. Okay, so we can say P by rho G plus V squared by 2G plus Z is a constant. This is what Bernoulli's theorem states that. But you can say here are 2 points. This is condition is 1 and this condition is 2. So when you write the equation, you can write like this: P1 divided by rho G plus V1 squared divided by 2G plus Z1. These are the inlet conditions over here. Inlet conditions over here. So you will be equal to P2 by rho G plus V2 squared by 2G plus Z2. Okay. Similarly, that means whatever flow water is entering over here, so that will be going out from here. So that means the total head of water will be, total head of water will be what? Total head will be constant. Head is constant. That is the value. Total head is constant. Okay, that is what the conditions we are saying that. Okay, that means conservation of energy. So it states that this P by rho G is known as the pressure head. P by rho G is known as the pressure head. V squared by 2G known as velocity head. And this Z is known as the height from the data. Height from that. So it states that a total head flowing through a pipe or an area is constant. So total head consists of pressure head will be there, velocity head and the height from the data. These are the 3 heads which will be over there. Okay. So it is based on conservation of energy of moving fluid. Okay. You may see this is the figure that I explained to you. Okay, so these are the concept, basic concepts you have to study in fluid. Okay, so I have already explained all those things. So we have to understand that fluid, actually the fluid, when it comes to fluid, the basic important thing is that it can be a laminar flow or turbulent flow, or in between laminar and turbulent flow. Based on this, there are streamlined flow, turbulent flow, streak flow, etc. So basically when you consider the flow is laminar or turbulent. So also we can see that when it comes to gas molecules, we can have compressible flow also. So these are the basic things which comes under our fluid chapter, and I have gone through the basic of these things. Okay, that problem part is not so important for you. Okay, we are just going through the basics, but we will discuss this in one of my classes itself. Okay, so one more thing, that last thing what we are going is that 3 laws. One is Archimedes principle. That means when a body is fully or partially immersed in a body, so in a water or a fluid, is borne up by the force equal to, whatever force is acting up will be equal to the weight of the fluid displaced. That means that is why shipping vessels etc. are floating in the water. It is based on the Archimedes principle. Then when it comes to Pascal's law, the change in pressure applied to an enclosed compressible fluid, when it is an enclosed compressible fluid, is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. Okay, that is what. Then Bernoulli's theorem states that, okay, so the total head of water flowing through a pipe or an area is constant, or a section is constant. That means the head consists of pressure head will be there, velocity head will be there, and Z, that means the height from the datum. So you can see here, this is P1, this is V1, this is, here you may say it as P2, V2, that is the output area. That is what they have explained here. They have taken this height as Y1 and the outlet height as Y2. Okay, so the water is flowing at the time T. At the starting, it is at T, and here that time taken is T plus delta T. But the total head is constant. That is a concept what they are going to derive from these things. Okay, so I think the concept is clear for you know these things.
Yes, sir. Yes, sir.
So these are the basic things what we are going to discuss in this fluid part. So if you have any doubt, please you may ask now. Okay. Then okay, then we will there are so many things when it comes to application of this Bernoulli's theorem. So one is known as Venturi meter, another one is orifice meter. Okay, these are used to calculate the discharge of flow. Okay, Venturi meter, orifice meter, etc. Okay, these are the applications of Bernoulli's theorem. They are, we can see these in large turbine plants, etc. Venturi meter, orifice meter. They are just used it to measure the flow rate. Okay, then there are so many equipments which you use this in fluids. One is orifice. Orifice is nothing but a small opening through which the water flows. Okay, these are fines applications, dams, retainers, etc. Okay, to identify the fluid flow or the calculate the discharge of flow, etc. So these things finds application in all those things. So there are some basic applications for Bernoulli's theorem. Okay, that is what we have already explained over here. So I think the concepts are clear. So we have got some laws, then what is fluid flow, what I mean by viscosity, we have discussed all those basic things. Okay, so if you have any doubt, you can ask me now, or otherwise we can stop the class, because we cannot discuss